In this video, we'll look at graphing piecewise defined functions. A piecewise defined function is a function that has different rules for different pieces of its domain. So it is a function that is comprised of pieces of different functions all on one graph. Piecewise defined functions are prevalent in everyday life. If you look at how we pay taxes, there are different rules depending on your income. If you think about like sending a package, depending on its weight, there's a price you pay, and maybe for a different weight you have to calculate the price in a different manner. So this is the way we represent having different situations of the same outcome. I have an example on the screen that is written like this. We read it as f of x is equal to, and then we have a big bracket, x plus 2 for x is less than or equal to -1, and x squared minus 1 for x is greater than -1. So notice that between x is less than or equal to -1 and x is greater than -1, that domain is all real numbers. But it's telling me to find the output value when x is less than or equal to -1. I'll use the rule x plus 2, that is y is equal to x plus 2. But when the input is greater than -1, I'm going to use y is equal to x squared minus 1. So I have a different rule for different pieces of my domain. Now notice also that there is only one output for every input of x, because a number will either be less than or equal to -1 or greater than -1. It can't be both. So depending on where the x value lies, these two function rules, only one of those will be used to calculate the output value. Now the corresponding graph, which we're going to work on in just a minute with getting these graphs, but notice that to the left of and including -1 on the x-axis, I have a point at -1, 1, then I have a point -2, 0, -3, -1, -4, -2. So this is an example of a ray, right? It's a line, part of a line, that goes to the x value of -1 and to the left. That line does not extend beyond the x value of -1. But then at -1, I have an open circle at -1, 0. Then it goes through 0, -1, 1, 0, and 2, 3. So notice that to the right of -1, my graph resembles a piece of a parabola, which hopefully that makes sense, right? Y equals x squared minus 1 is one of those basic functions, and it's shifting down the x squared 1 unit. But why do I have an open circle at the -1, 0? Well, think about what values of x this second rule applies to. Anything larger than -1, so -0.9, -0.99999, right? I can get so close to -1, I'm basically touching it, but I have to use the open circle to show that it's not truly defined at -1, but everything up to the -1. So every number between 0 and -1 is using the second rule, which is why I need to have the graph between those values. So don't just think integer values when you're graphing these. We have to think about decimal values and all those numbers in between. So in this example, I want to graph a piecewise defined function, and we will state its domain and range. We have the function f of x is equal to, in this brace, x plus 2 for x less than 1, and 4 if x is greater than or equal to 1. The way I like to do these is actually to break them apart to make two different function tables. So I'm going to make a column for x and state my restriction. So this table is only valid when x is less than 1. The y value I will call y sub 1 is equal to this function rule, which was x plus 2. And then we'll look at the corresponding ordered pair x, y sub 1 for that piece. Then I make another table for x, but I define the restriction, and that is that x has to be greater than or equal to 1. And then my rule for this function is that y is equal to 4. So we'll call this y sub 2 equals 4, and then we'll have the corresponding ordered pair. So in my first piece, x has to be strictly less than 1. But by the reasoning I was just stating before, I can't list all of these numbers less than 1. Right, 0.5 is less than 1, 0.6, 0.8, 0.9, 0.99999. So again, I have to actually use the boundary of the 1, but I will indicate that it has to be an open circle because x is strictly less than. So if you have a less than or greater than, your endpoint will need to be open. But then my other values of x in my table have to be less than 1. So any values less than 1, so I'll put in 0 and negative 1. Then we find our y value just as we've done with plotting points before. So if y is equal to x plus 2, when x is 1, we get y is equal to 1 plus 2, or 3. When x is 0, we get y is equal to 0 plus 2, or 2. And then when x is negative 1, we get negative 1 plus 2, or 1. So we have the ordered pairs 1, 3, 0, 2, and negative 1, 1. I'll go ahead and plot these on my coordinate system. I plot 1, 3, but be careful, I have to plot it with an open circle. 0, 2, and negative 1, 1. So this falls in the shape of a line. Don't get carried away though. That open circle at 1, 3 says I can't go beyond it, right? Because this rule is not defined for values greater than 1, only less than 1. So I'm going to connect these points to the left of 1, 3 to show that I have this part of a line. Now my second piece says x has to be strictly greater than or equal to 1. So I need to include 1, right, because that is the endpoint. But this time it is included in my domain. So because I have greater than or equal to, I will have a closed point at this particular ordered pair. So if you have a less than or equal to or greater than or equal to, your endpoint will be solid or closed. Then I can choose any other values that are greater than or equal to 1. So I have 2 and 3. My y value, though, for these particular pieces of x is just 4, right? So y is equal to 4 when x is equal to 1. Y is equal to 4 when x is equal to 2. Y is equal to 4 when x is equal to 3. So the corresponding ordered pairs are 1, 4, 2, 4, and 3, 4. Plotting these, 1, 4 is a solid dot, 2, 4, and then 3, 4. So this resembles a part of a horizontal line, but I cannot go to the left of 1 because this piece is only defined when x is greater than or equal to 1. So I connect the points to the right of this 1, 4. So notice that my domain is all real numbers. If I go from left to right, this first piece goes from negative infinity up to 1, which is really not included, but my second piece starts at 1 and goes to the right to infinity. So everything from negative infinity to infinity is in my domain. Remember, your range is from bottom up. So the bottommost value, right, where does this graph go in a downward direction? It continues down to negative infinity. And then it goes up to this y value of 3, but that 3 is not really included because of the open circle. So we write 3 with the parentheses. And then union, what about the y values for the second piece? There's only one y value on that horizontal line segment, and that is 4. So we would say union and then a set notation, 4. Another example is f of x equals, and then in this bracket, negative 2 minus x, for x is less than negative 1, and negative 1 plus 3x, for x is greater than or equal to negative 1. So again, if I'm graphing this by myself, by hand, I would make two tables. I would label my headers x, but I would state the restriction that x has to be strictly less than negative 1. And then I would state what y is equal to. So the first y value is negative 2 minus x. And then in my second table, I have x, but it's defined only for x greater than or equal to negative 1. And the y value for that piece is negative 1 plus 3x. So in my first chart, I have to put the endpoint of negative 1, right? Because there are infinitely many values less than negative 1 that are between negative 2 and negative 1. So I still have to put negative 1, but it has to be an open circle because of that strict less than. And then my other values need to be selected by choosing something that's less than negative 1. So negative 2 and negative 3, right to the left of negative 1. Well, my y value is found by plugging into negative 2 minus x. So when x is negative 1, I get y is equal to negative 2 minus, in parentheses, negative 1, which is negative 2 plus 1, or negative 1. When x is negative 2, I get y is equal to negative 2 minus, in parentheses, negative 2, which is negative 2 plus 2, or 0. And then when x is negative 3, negative 2 minus negative 3 is negative 2 plus 3, or 1. So we have the ordered pairs negative 1, negative 1, negative 2, 0, and negative 3, 1. Plotting these, negative 1, negative 1, we have an open circle at that point. Negative 2, 0 is on the x-axis. Negative 3, 1. So notice that just from the equation, I knew this was a part of a line, right, because it's y equals mx plus b. To graph this piece, I'm going to extend the line downward through these points, negative 3, 1, negative 2, 0, but I have to stop at the negative 1, negative 1. I cannot go beyond that point because the function isn't defined according to this rule to the right of negative 1. Now, my second piece, or second table, I will put in values greater than or equal to negative 1. So I'm going to put negative 1, since that's my endpoint, and I have to put a solid or closed circle since x is greater than or equal to that value. Then any other values of x which are greater than negative 1, so 0 and 1. The y value then is negative 1 plus 3 times x. So negative 1 plus 3 times negative 1 is negative 1 minus 3, or negative 4. If x is 0, we get y is equal to negative 1 plus 3 times 0, which is negative 1. And when x is 1, we get negative 1 plus 3 times 1, which is negative 1 plus 3, or 2. We have the ordered pairs in negative 1, negative 4, 0, negative 1, and 1, 2. So plotting these, -1, -4 with a solid dot, 0, -1, and 1, 2. So again, this is another part of a line, but I have to extend it to the right only of -1, -4. I cannot go beyond, that is, I can't go to the left of -1, -4. So my graph is two pieces of two lines. What is my domain? It goes to the left, extends infinitely to the left to negative infinity. The first piece stops at -1, not including it, but the second piece picks up at -1, including it, and continues to the right. So that actually covers all real numbers, negative infinity to infinity. The range from the bottommost point, this -1, -4 is my bottommost point. So my range is that y value of -4. And notice the graph extends infinitely up to infinity. But the left piece actually is already included in all of those range values, right? It's from -1 to infinity. So all of those are already included in this particular range. Now, you can actually graph a piecewise defined function on the calculator. I have some illustrations here with some screenshots for you. That first function where we had y is equal to x plus 2 for x is less than 1, and 4 for x is greater than or equal to 1. You have to input these into two different equations in the calculator, and you have to define the function and the piece of the domain. So the way we do that is we put the function rule in parentheses, and then we're going to do a division symbol, and I'll explain why in just a minute, and then we'll put in parentheses the restriction on x. So x is less than 1. To get the inequality symbols, you're going to press second in math, which is the test menu, and then you're going to choose the appropriate symbol. And then you'll repeat that. The second function you'll put in parentheses, divided by, and then the restriction on x. And then you can press graph. The thing about this is it won't tell you clearly if you have a closed or open circle on the graph, so you need to know that. But when you look at the table by doing second graph, you can kind of tell. X plus 2 is defined where x is strictly less than 1. So notice at 1, we get an error message. So that would tell us we need to have an open circle. We get an error message in the y1, but in the y2, we get the value 4, so this would tell you that it's closed there. So in the other case that we just did by hand, y equals -2 minus x for x is less than -1, or -1 plus 3x for x is greater than or equal to -1. Again, you can put the function in parentheses, divided by, and then the restriction on the domain for each of those rules. I didn't explain this before. We put the division sign because what's going to happen is that if the x value is less than -1, it assigns a 1 to that number or to that expression. If it's not, it assigns a 0. So it's either going to be dividing by 1 or 0, which tells you then where the function is going to actually be graphed. And you can pause this video to explore how to do this in more detail. Now you're going to see some examples of piecewise defined functions. So here's one. And when I say examples, I mean applications of these. The tuition and fees of a certain college are based on the number of credit hours a student enrolls. Students who enroll in up to 5 credit hours are charged $401 per credit hour, plus $202. Students who enroll in 6 to 14 credit hours are charged $291 per credit hour, plus $1,064. Students who enroll in 15 or more credit hours are charged $5,429. So we want to write a piecewise defined function that represents the total tuition and fees for enrolling in X credit hours, and then determine the tuition and fees for a student who enrolls in 4 credit hours, 9 credit hours, 12 credit hours, and 18 credit hours. So notice there are several different cases we're given. We're given students who enroll in up to 5 credit hours, students who enroll in 6 to 14, and students who enroll in 15 or more. So my function we can write in this way. F of x is equal to, so we'll have 3 pieces. Our restrictions are if x is between 1 and 5, then x is between 6 and 14, and then x is greater than or equal to 15. And we were told the rule that you had to pay $401 per credit hour and then plus the $202 in fees. For the second rule, it was $291 per credit hour plus the $1,064. And the third case was it was just a flat rate of $5,429. So f of 4, we have to figure out, well, which piece does a 4 lie in? That is, which part of the domain does a 4 lie in? 4 is between the 1 and the 5. So we use this first rule. F of 4 then is 401 times 4 plus 202. And we get $1,806. F of 9, well, 9 is between the 6 and the 14. So we plug into the second rule, which is 291 times 9 plus 1,064. And we get $3,683. F of 12, 12 is still between the 6 and 14, so we use the second piece. 291 times 12 plus 1,064. And we get $4,556. And then F of 18, well, 18 is greater than or equal to 15. So my function rule says the tuition and fees is just $5,429.